Hey, it's Brian, and I'm going to present as a set of annotated slides, this set of in-person slides about the meaning of life. And I apologize for this, because this is one of my favorite classes to give in person. And for folks who are in the Monday section, I would say come to the Wednesday section. We will make room for you. There will be room if you would like to see this in person. But there is some information in here that you definitely want to see. And there's some information in here that I definitely want you to see. But I'm going to start with this question. Here's a poem by Robert Frost. It's called Fire and Ice. Some say the world will end in fire, some say in ice. From what I've tasted of desire, I hold with those who favor fire, etc., etc. So here's the question. Does the world end in fire or ice? What do you think? Fire or ice? And the interesting thing is there's been some trends over the years. And this is something that I will ask folks in class. And I will talk to people about that on Wednesday, and I'll let you know what everybody says. And by the way, this is a question that we are going to answer at the end of class today. We will get to a point of being able to say something substantive about that. But before I do that, I want to do another installment of things I like about your generation. And here's one thing I just love about you people. You are very open. Okay, in years gone by, when people were experiencing difficulties or stresses or whatever, they wouldn't tell me what was going on, and it made it really, really hard to be able to understand what people were going through. But you folks are very open about everything that you're going through and all the things that you're thinking, and I really appreciate that. It helps me get to know you better, and the more I know you, the more I like you. So thank you much for that. Now today, we're going to be talking about heat, but I want to distinguish between heat versus thermal energy. Okay, thermal energy is a form of energy like kinetic energy or potential energy, etc. Heat is a transfer of energy. Remember, when we had that basic model, we had the system. Heat was a transfer of energy into the system or out of the system. So heat's a transfer, and that's important. And my analogy is this. Thermal energy is like money. Heat is like Venmo. Okay, I'm going to Venmo you something. That means like I'm going to take some money, but I'm going to transfer it to you. And the heat is actually the transfer. It's energy, but it's being transferred. And that transfer we call heat. Now, when you add heat to something, the temperature goes up. You know that this is true. That's one of the most basic things that happen when you add heat to things. And we have some relationships that describe this. And the ones we'll use are this, okay? The change in thermal energy is equal to m times c times delta T. This works if you have some sort of internal transformation. So inside a system, if you have an increase in thermal energy, and that'll happen like if inside the system you're going to have kinetic energy goes to thermal. We've seen cases where that happens. You're going to have a temperature rise. The other equation we have is Q is equal to m times c times delta T. If I have some sort of a system and I add heat to it, the temperature will change. But that's very different. The first is an internal conversion. The second is an external addition. Okay? And this is something I'm sure that you've seen previously. And the crucial piece of the puzzle is that in the relationships that we have for the change in temperature, we've got one, the mass of the object, m, two, the specific heat, and that is a material property. We have a table of specific heats in the textbook that we will use to solve problems. And let's solve, there was a first problem that I actually looked at, and this was in the annotated slide videos, where we said, if you catch a fever, or catch the flu, and you have a fever, and your temperature goes up from 37 to 39 degrees Celsius, the question was, how much energy is required to raise a person's body temperature? And it turns out it's about 0.48 of a little Juan burrito. It's a lot. It's a lot of energy to raise your temperature because, one, your mass is not small, and two, you're made mostly of water, and the specific heat of water is quite large. And now I want to come back to this question about pronghorn that we saw on a previous homework assignment. So here's the thing, pronghorn, when they run, and when you run inside your body, the energy transformation that's happening is chemical energy is turning into thermal energy in your body. We've said that that's exactly 100% of what's happening. And so if chemical energy is turning into thermal energy inside your body, your temperature is going to increase. Temperature is going to increase. And you can only have your temperature increase so much, and then you just have to stop exercising. So if you want to keep exercising, what you need to do is figure out some way to exhaust heat into the environment. And the way that you do it or one way you do it is by sweating. And we are good at that. We're really, really good at keeping ourselves cool at sweating. And that's actually one of the things that makes us such a good endurance predator, is we can keep ourselves cool by exchanging heat from the environment by sweating. And that's one of the modes of heat transfer that we talked about in our second set of annotated slides, was evaporation. If you have a hot object, liquid water in or on the object evaporates and turns into water vapor. That carries heat away. But there's other modes that we're going to look at in those slides: conduction, convection, radiation, and I'm particularly concerned with conduction and radiation. Now, if you are evaporating water, the amount of energy it carries away is given by the heat of transformation. Okay, and this is talked about in the textbook. You also looked at this in the set of annotated slides. The main one we're going to consider is this one right here. Water doesn't have to get up to 100 degrees Celsius to turn from liquid to vapor on your skin. You know this. It just evaporates. And at skin temperature of about 30 degrees Celsius, the heat of vaporization is 24 times 10 to the 5th joules per kilogram. This is a number we'll use quite a bit. And a kind of problem we'll solve, we'll see in a minute. But first off, I want to think about this. You can keep cool even when the outside temperature exceeds the maximum body temperature. Okay, so check it out. Here's this young lady, and the temperature is 110. I've certainly been places where the temperature is that high. So the air is transferring heat into your body because it's warmer than you. How are you able to keep cool? And the answer is you keep cool by sweating. You're evaporating liquid from the surface of your body, and that carries heat away, and that evaporation keeps you cool. And that's what Milo is doing when he's panting. When Milo is panting, what he's doing is he's making air move over his tongue, he's getting more evaporation, and he's taking heat out of his body. That's what that's all about. And there's also this demonstration that I did in the first day of class. And if you show up in person on Wednesday, I will do this. I will set a pile of flash cotton in my hand on fire. And the way my hand keeps cool is because water on my hand evaporates, and that helps keep it cool and keeps it from getting burned. And it's also the reason for this little demonstration. And we have a little video on the Little Shop of Physics website where you have this little creature we call Flamehound. And we call him Flamehound because he's sitting there happily in this kind of like little nest of fire. And we put on him a little mix of alcohol plus water. The alcohol burns, the water evaporates. And so Flamehound is immersed in flames, but is staying cool because of the evaporation of the water. By the way, something quick to note. We put this video out, and sometime after that, this internet meme showed up. And I like to think that we might have had a little piece of that showing up on the internet. Moving on, here's something to be aware of. One of the big issues we're going to have with climate change as the planet warms is this. A lot of places are getting warmer, but they're also getting higher humidity. And if we have a 10 degrees Celsius increase, which we could if nothing changes in the amount of fossil fuels that we burn. The temperatures have been that high at times in the past. You will have large regions of the globe, like all these regions here, that become uninhabitable. The temperature is so high and the humidity is so high that you can't keep yourself cool by evaporation. You will die if you are outside, which is kind of a scary thing to think about. Not just that it got hotter, but we've rendered portions of the world uninhabitable. That's kind of a crazy, crazy, scary thing. Something else I want to bring up with evaporation is this. When plants are actively respiring, they are sending water up into the atmosphere. Okay, they're sending water up into the atmosphere, and when that happens, they're actually cooling the earth. And so we have a time, and you will see this. We've just had a heavy snowfall. The plants are going to stop exchanging. They're going to go dormant. They'll stop exchanging water with the atmosphere. And when that happens, you're going to see a so-called second summer. You're going to have a rebound. The temperatures will rebound. Watch for that. Once all the snow melts, the temperatures will go up, and we'll have this kind of like echo of summer, and it's because the plants have stopped doing their thing. And so as a consequence, we're not getting as much evaporation from the surface of the earth, and the temperatures can get higher, because really when the plants are sending water into the atmosphere, that keeps the earth cooler. Now, let's do an example of a problem and the type of problem that we're going to look at that connects the stuff we've been doing with energy with the things that we're doing right now, which have to do with thermal energy, okay? So suppose you're bicycling at a good clip and you're using 400 watts of metabolic power. As you exercise, your body starts to warm up. You perspire to keep yourself cool. Okay, we assume your body is 25% efficient. And the question is this: how many joules per second of thermal energy will your body gain if you have no means of exhausting excess thermal energy? And then 2, assuming that you can dump that energy into the environment as heat by evaporating water, how much water would you have to evaporate during a 1-hour ride? Okay, these are the questions that we're going to consider, and we'll start by strategizing. And for strategizing, first off, we'll say the first part of the problem right here, okay, using 400 watts of metabolic power, we're assuming your body is 25% efficient. That's kind of like a using energy kind of problem as we saw previously. That's the kind of thing we saw in chapter 11 on using energy. That's our first piece. The second piece of the puzzle, well, how much water you have to drink, how much water you have to evaporate to keep yourself cool, that is a question of thermal energy. And that's a question, that's the type of thing we're considering in chapter 12. Now let's do some preparation. So your body's the system, and inside your body, every second you're using 400 joules of chemical energy. But your body's 25% efficient, and what you're getting for that expending chemical energy is 100 watts or 100 joules per second to make you go forward. And the energy that you expend that way goes into basically the kinetic energy of moving air. You have to push air aside, and the energy actually goes into the air, or else you lose some due to friction with the road surface, and that's lost as energy in the road surface. But you're basically using 100 joules to go forward. That's the first piece of the puzzle. So since that's true, 300 joules basically stay inside your body. 300 joules are going to stay in your body as thermal energy. So every second, you're going to increase your thermal energy inside your body by 300 joules. Okay, that's true. Now, next piece of the puzzle is we want to consider how do you keep yourself cool. If you're doing it by evaporation, how much water would you have to evaporate? And so we're saying this: if you have to get rid of 300 joules every second, that means in one second, you have to exhaust 300 joules of energy into the environment as heat. So you got to lose 300 joules of heat. That's our preparation for the next step. In the next step, we're going to do our solution. Now, the ride that you're doing is 1 hour, okay? And 1 hour is equal to 3,600 seconds. And each second, the amount of thermal energy your body is picking up is 300 joules. So you're picking up 300 joules per second. And so the energy that you have to exhaust, the heat that you have to lose, is 300 joules every second for a time of 3,600 seconds. And so the amount of heat that you have to exhaust into the environment is 1.08 times 10 to the 6th joules. And you do that by evaporating water. Okay, when you're evaporating water, our basic relationship was this: Q is equal to M times LV. Now LV is the heat of vaporization of water, and at skin temperature, that's 24 times 10 to the 5th joules per kilogram. The amount of heat that you have to exhaust is 1.08 times 10 to the 6th joules. The only thing we don't know is the mass, and so we can solve for the mass. And if we do that, we get 0.45 kilograms, which means since 1 kilogram of water has a volume of 1 liter, the amount of water that you have to get rid of is 0.45 liters, so half a liter of water every hour. And that seems reasonable. This is not a particularly hard ride. That's you're bicycling at a pretty gentle clip on a warm day, and you have to drink half a liter per hour. I mean, that certainly seems quite reasonable. And in fact, you'll probably have to drink more than that. we've made some assumptions in our calculations, but that's the number that we get, and it seems quite reasonable to me. Now next I want to talk about efficiency, and I want to look at two different situations. We talked about the idea that you can convert thermal energy to other forms of energy, but you can't do that with 100% efficiency. For instance, this power plant right here is about 40% efficient. That's typical for a power plant, and no plant does much better. That is a fundamental limitation. That is due to something that is baked into the fabric of the universe. But there's also process limitations. It costs you energy to walk a certain distance. It just costs you energy to walk. But that really is a function of how you're built. And so we could build you differently, and you would be able to walk more efficiently. For instance, kangaroos can bounce a 10-kilometer distance using half the energy that it would take a human of the same size to run that distance. Kangaroos are just more efficient than you are. And they're efficient because they store energy in stretchy tendons in their legs, okay? And you can also be more efficient by getting on a bicycle. And if you're on a bicycle and you're rolling, you use a lot less energy to travel those 10 kilometers, even less than a kangaroo. But today, I want to talk about those fundamental limitations. And the reason we have those fundamental limitations is thermal energy is special. We've talked about this previously. You have a lot of transformations of one kind of energy or another to thermal energy, but it doesn't go back. When the plane stops on the tarmac, you're going to lose energy to thermal energy as the plane skids to a stop, but you can't take an airplane, put it out on a hot patch of asphalt, and have the thermal energy turn into kinetic energy as the plane is hurled into the sky. You know that doesn't happen. There's a one-way transformation of energy to thermal energy, and it doesn't go back. And if you want to make it go back using a heat engine, using a power plant, you can't do that with 100% efficiency. Because there's something special about thermal energy, and what's special is thermal energy has entropy associated with it. And entropy is a word you've probably heard of before. And you can think of it as a measure of disorder or randomness. And if you look at two situations here, if I have a baseball, cold baseball, and I've hurled it at fastball speeds, all the molecules inside the baseball are moving in the same direction. That is a very orderly situation. If I consider a warm helium balloon, and it turns out the total energy of the atoms in the helium is about equal to the total energy of all the atoms inside a moving fastball, so it's about the same amount of energy, but it's very different because the thermal energy of the balloon is all the atoms inside there are moving every which way. They're moving at random speeds and they're moving in random directions. And so it's very, very disorderly. I end up with a very orderly motion here and end up with a very disorderly motion here, okay? And we can think of entropy that way. It's a lack of order or randomness, okay? And here's the second law of thermodynamics. The entropy of the universe always increases, okay? So energy is conserved. Entropy is not. It is always increasing. So it's like whatever the opposite of conserved is, it's just always getting greater. And this fact limits the efficiency of the heat engine. The reason why you can't convert 100% of the thermal energy pulled from the hot reservoir into useful energy output is that when you pull in thermal energy, when you pull in heat, you pull in a certain amount of entropy. And then in order for the entropy, that would decrease the entropy of the universe, and you can't do that. So you have to increase the entropy of the cold reservoir in order to be able to extract some of the thermal energy and turn it into useful work. So as a consequence, there's a maximum possible efficiency of a heat engine. Now, you can increase the efficiency, though, because the efficiency is related to the temperature of the hot reservoir and the cold reservoir. So I want you to take a second and think about this. Which of the following changes would allow a heat engine to run more efficiently? Go ahead and pause the video, take a second, think about it. I'll be back. And of course, given the relationship It's 1 minus Tc over h. And I want Tc over h to be as small as possible. And I can do that by decreasing the temperature of the cold reservoir or increasing the temperature of the hot reservoir. A or D will make a heat engine run more efficiently, and that's why I have this picture here. This is a solar concentrator focusing sunlight onto the hot reservoir, basically, of a little heat engine, and then the other end is basically at atmospheric temperature. You can get temperatures here as high as 600 degrees Celsius, and that gives you a very, very high efficiency. Now, entropy also limits the efficiency of a heat pump. If you are taking energy, thermal energy, and you're moving it from someplace cold to someplace hot, it turns out if you just moved it straight away, that would imply a decrease in entropy. So as a consequence, you've got to do work to make that happen, because when heat flows from a hot place to a cold place, which is the natural flow, that increases the energy of the universe. And so if I reverse the natural flow and made it go from cold to hot, that would decrease the entropy of the universe. You can't do that. And so as a consequence, you have to put in work to make that happen. And the work, any energy that you put in, turns into additional thermal energy in the hot reservoir. That's how you keep the entropy of the universe from decreasing when you move heat from a cold place to a hot place. But you can increase the efficiency of a heat pump. If this is our equation for the coefficient of performance for a heat pump used for cooling, which is the kind you have in your refrigerator, you can make it run more efficiently. And what changes would you make? Go ahead and take a look at this. Pick one or more of the answers. I'll be back. Well, if I want this expression here to be as big as possible, I want the denominator to be small. So I want the difference between TH and TC to be small. And I do that by either decreasing the temperature of the kitchen, which decreases TH because that's the hot reservoir, or increasing the temperature inside of the refrigerator because that's TC, that's the cold reservoir. So I just want to decrease the difference in temperature between the inside of the refrigerator and the outside of the refrigerator, and that helps you in two ways. One, if you decrease the temperature between the inside and the outside, less heat goes from the inside to the outside, and then you have to pump less heat out. But the other thing it does is it actually renders the heat pump more efficient. Now here's something to be aware of. The second law of thermodynamics, says that when you run a heat engine, you have to deposit heat into the environment, as we talked about. That's the second law of thermodynamics. There's nothing you can do about that. But there's no law that mandates that the heat has to be wasted. You're depositing heat in the environment. Why don't you use it for something? And I'll show you some examples. Right here, this is the Blue Lagoon, and it's in Iceland, and it is the most popular tourist attraction in Iceland. And it's a bunch of warm water, and people are just like soaking in the warm water, because who doesn't love soaking in warm water? This warm water is actually the cold reservoir for a power plant. There's a geothermal power plant that pulls heat from deep underground, pulls in QH from underground. You extract some useful work, then you deposit heat into this cooling pond. And they just figured, well, it's this cool color of blue because of minerals in the water, and let's let people soak in it. And people pay a lot of money to be able to soak in this warm water. But it's not a natural hot springs. It's the cold reservoir for a power plant. Very, very cool. But another thing you could do is this. If you have a power plant and you're using coal to generate electricity, you burn the coal, you create thermal energy, you can convert some of that to electricity, but you have to deposit heat into the environment. But why not, rather just like dumping it in a nearby river, why not putting it in people's homes and letting people use it to warm their houses? And let's do a calculation. Okay, so 560 megawatt coal-fired plant uses thermal energy from burning coal to heat steam to 370 degrees to run a turbine. The plant is cooled by water in a nearby river to 10 degrees Celsius. Question, what is the minimum power the plant must deposit in the river? And by the way, these are real numbers for an actual power plant. And then say, instead of depositing that power in the river, let's send it out to people's homes. And in cool seasons, in a temperate climate, it takes about 300 watts of heat to keep your house warm. So how many houses could you heat with the so-called waste heat? Let's take a look at that question. And we start by strategizing. And by strategizing, I'm just going to say this is a heat engine question. So if I have a heat engine and I'm pulling in heat from the hot reservoir, I'm dumping heat into the cold reservoir, and I'm getting useful work output. That's my basic diagram of a heat engine. And by the way, this useful work output, that's the 560 megawatts. You rate heat engines by the energy, or you rate power plants by the energy that they put out. Okay? So we need to calculate what QC is. Okay? That's our strategy. Next, we can do some preparation. And for preparation, I'll remember that the efficiency of a heat engine, which this is 1 minus Tc over Th. And Tc and Th are the temperatures of the cold and the hot reservoirs. And remember, those have to be in Kelvin. So the temperature of the cold reservoir, 10 degrees Celsius, or 283 Kelvin. Th is the temperature of the hot reservoir. That's the temperature of the steam, which is 370 degrees Celsius, which is 643 Kelvin. And if we work out what the efficiency is, we get an efficiency of 0.56. And now we're ready to solve. So remember, our heat engine looks like this. Okay? So we are pulling in heat from the hot reservoir. We're dumping heat into the cold reservoir. And let's just do 1 second. Okay, in 1 second, the plant is putting out a work of 560 megajoules. Okay? That's my useful energy output. The efficiency, if we assume it's working at its maximum theoretical efficiency, and in fact it will be working at less than that because there are certain practical limitations, but let's suppose it's working as efficiently as it possibly can, the efficiency is 0.56. It's what you get divided by what you had to pay. Well, what you get is the useful electricity output. What you had to pay is the heat that you get from burning coal, because if I need more heat, I've got to burn more coal, and I literally have to pay for that. So it's what you get divided by what you had to pay. And so I can work out what QH is. And if I do that, I get QH is equal to 1,000 megajoules. Okay? And if I know QH is 1,000 megajoules every second, and so I pull in 1,000 megajoules, I take out 560 megajoules, and that turns into useful electricity. How much do I have to deposit in the river? Well, the answer is, in the cold reservoir, the river, I have to deposit 440 megajoules. Okay? And here's the question. How many homes could that heat? Well, it's 450 megajoules in 1 second. So that corresponds to a power of 440 megawatts. And if I take that 440 megawatts and I divide it by the 3,000 watts necessary to heat a home, what I get is that you can heat 140,000 homes. That's like every home in Larimer County. And that's with the waste heat from a coal-fired power plant. And so Europe has a lot of these combined cycle plants where they generate electricity, but as a part of generating electricity, you generate this thermal energy. You just take it and let people use that to heat their houses. The other entity I know that does this is CSU. CSU has a power plant that they use to provide hot water to buildings for heating. And the hot water comes from the generation of electricity. And it's actually just on the oval. It's actually right near to Johnson Hall where lectures are. So the energy that's actually heating the lecture hall is the waste heat from generating electricity, which is kind of awesome. And there's no rule that you can't do this. We don't much in the United States. And I think it's probably because the people who sell us the gas for our heating and the people who sell us our electricity for doing other things in our house are different entities. But if you can get all of your energies from one place, and if there's an emphasis on efficiency, this is absolutely the way to go. We should do more of this sort of thing. Now I want to talk about some philosophy, and I want to talk about three things. One is the arrow of time, two is the meaning of life, and three is the end of the world, okay? And I'm going to make some broad brush assertions, but basically I'm telling a story. I'm telling a story of the second law of thermodynamics. I want to be aware of there are other stories. So when I'm talking about the meaning of life, I mean this in somewhat of a tongue-in-cheek fashion. So I don't want to cause anybody any offense. There are other stories, and I respect those deeply. But this is one story that you can tell, and it's a story of thermal energy. It relates to the second law of thermodynamics, and at its core, the second law of thermodynamics says heat spontaneously goes from hot to cold. If I have something warm, it will send heat to the environment which is colder. That is the spontaneous way for heat to go. It won't go back. And that fact that heat always flows from hot to cold, that the entropy of the universe always increases, that you can't have a heat engine with 100% efficiency, that's the second law of thermodynamics. That is the only law of nature that has a preferred time direction. Think about it. Energy is conserved. The amount of energy in the universe is the same. And what that means is there's no difference between the past and the future as far as energy is concerned. The past and the future are exactly the same. And if everything was conserved, nothing would ever change. There's no difference between the past and the future. And the only thing that doesn't work that way is entropy. The entropy of the universe is always increasing, and that is the only thing that differentiates the past from the future. In the future, the entropy is higher. No other fundamental law of nature distinguishes between the future and the past, and that's crazy but true. Now I want to think about entropy a bit more, okay? When I say it's orderly, I mean that literally. So I take a look at these two boxes. Take a look at these two objects. I got a hot object in red and a cool object in blue. I put them next to each other. They are ordered. I can distinguish between the two sides. I can say the hot one's on the left and the cool one's on the right. Box 1 is on the left, box 2 is on the right. I can order them. But what happens if you put a hot object next to a cold object? Heat is transferred from the hot one to the cold one. And that will happen until they reach the same temperature. And when they reach the same temperature, now you can't tell the difference, which is box number 1 and which is box number 2. I can't tell. I could switch them and the situation would look exactly the same. I can't tell the difference. They are disordered, which means I can't order them. It means literally I am unable to order them. The ordered situation is low entropy. The disordered situation is higher entropy, and the universe will naturally progress from the orderly situation to the disorderly situation. Now, when you transfer one form of energy, like kinetic energy, into thermal energy, you increase the disorder, you increase the entropy. And once energy is transformed to thermal energy, it doesn't go back. And I have a class, I'm going to show a series of videos of me doing different things. And if I'm doing something where I'm turning like kinetic energy into potential energy, you can't tell if I'm playing the movie forward or backwards. If I have a movie, if I'm doing an activity where I turn kinetic energy into thermal energy, you can tell. Because kinetic energy goes to potential energy completely reversibly. Forward and backward in time doesn't make any difference. But this kinetic energy to thermal energy is not reversible. You can't reverse it. And so as a consequence, you can tell that that video was played backwards. The arrow of time is in the future, entropy is higher, and once you convert one form of energy into thermal energy, it doesn't spontaneously go back. Entropy is higher in the future. And this is what defines the arrow of time. Quick aside. I think love is like entropy. Years ago, I used to use an analogy in class. I said, like, love is like energy. And somebody came up after class and said, no, love is like entropy. And I said, what do you mean it's like entropy? And they said, well, energy is conserved. Love is not conserved. Over time, it can just grow and grow and grow. And if you give love to someone, that doesn't mean that you have less. It might mean that you have more. And so I feel like love is like entropy. It could just increase with time. Here's a picture on our honeymoon of me and my wife Carol, and here's a picture of us on a trip 31 years later. Same thing, taking pictures in a mirror. This was how we used to do selfies back in the day. And here's us taking a picture in the mirror, and you can see love has just increased with time. And giving love to someone doesn't mean that you have less. In fact, it means that you have more. Now, I want to talk about the meaning of life, and I mean this in a thermodynamic sense. And here's the thing. As time goes on, the entropy of your body increases. Things break down, things wear out, things fall apart. To stay alive, you absolutely must reduce the entropy of your body. You have to do that because it will spontaneously increase. It'll become disorderly, and that's not good. How do you stay alive? What you do is you take in high quality forms of energy and you exhaust them as heat into the environment. And when you exhaust heat into the environment, I am increasing the entropy of the universe, and I am decreasing the entropy of my body. And that's how you keep your entropy constant, is you eat high quality forms of energy and you deposit heat into the environment. You increase the thermal energy of the environment. So you're basically turning chemical energy into thermal energy and dumping it into the environment. That is one way to define life. Anything that is alive, okay, on the planet takes high quality forms of energy, like solar energy or chemical energy, and degrades it into low quality or high entropy forms of energy, okay? And here's the thing. This is basically a definition of life. And so when you eat, don't ever feel guilty about eating. When you have a snack, what you are doing is you are fighting the demons of disorder. Don't feel guilty about eating. You have to eat to live. And so this monkey is saying, like, demons of disorder, come here. I banish you. I discard you as heat into the environment. Don't feel guilty about eating. You must do that to eat, to live. And that is something that all life does. All life takes in these forms of energy, deposits heat into the environment. That's the meaning of life from a thermodynamic perspective. You have to eat to live. You take in chemical energy, you deposit heat into the environment. That is necessary for life to continue. But there's more to the story. And I want to think about this. If the entropy of the universe always increases, why do things appear so orderly? And I took a picture of this flower. Here's a really healthy ecosystem that I was hiking in, and it just looks orderly. I mean, there's like flowers and plants and things like that. Things are nicely ordered. I can tell, like, oh, here's a flower, here's a green thing, here's mulch, leaf litter. It's orderly. It is not just like undifferentiated. So how do things get so orderly if the entropy of the universe increases? And let's think about this. And I want to talk about entropy and how it relates to ecosystems. Question for you. Which has a higher entropy? A desert or a rainforest? Take a second and think about that. And remember, entropy works this way. Low entropy means orderly. High entropy means disorderly. You can't order things. And if you look at a rainforest, like a healthy patch of rainforest, one of the things that distinguishes it is that the temperature is basically uniform everywhere. What that means is high entropy. If you look at the desert, I'm going to have hot spots and I'm going to have cold spots because of shade, et cetera, et cetera. Deserts have huge thermal gradients. As a consequence, they are orderly. They have low entropy. Here's a picture of Houston, Texas, not a healthy ecosystem, and you can see huge variations in temperature. Here's a picture of patches of rainforest, and you can see in a thermal image, this is a thermal image, you can see over here very uniform temperatures. Over here where people are carving into the forest, I'm getting differences in temperatures. That is not a healthy ecosystem. Over here it is. And you can actually use the evenness of the temperature distribution, i.e. the entropy, as a measure of the health of an ecosystem. High entropy means healthy. The more diverse an ecosystem, also, the higher the entropy. Okay, diversity in an ecosystem means higher entropy. It means more uniform temperatures. It's kind of an amazing thing. And when you have life, okay, It's very, very orderly. But because of the existence of life, and the more diverse it is, the more this is true, it increases the entropy of the universe. So life, like you, is about, like things that are alive are actually pockets of low entropy. But they're agents of entropy increase. Anything alive is increasing the entropy of the universe faster than if that thing was not alive. So if you look at Mars, Mars has much larger temperatures between day and night than Earth. That's orderly. You can tell the difference between the two sides of the planet. Earth is alive. Earth has life, and because of that life, it moderates the temperature differences. And so as a consequence, Earth, with its diverse living ecosystems, has higher entropy than Mars. And it's because of life. Life increases entropy. And here's another way to think about it, the meaning of life, okay? You are a patch of order in a disorderly world, but you serve the cause of disorder. Here's Carol and me, and we're eating these awesome little soupy in bread bowl things in Slovenia, and we are exhausting heat into the environment. We are actively serving the cause of disorder. Brian and Carol, agents of entropy, absolutely. And now I want to talk about the end of the world. I started class by saying, like, will the world end in fire? Or will it end in ice? Which one? Fire or ice? Which one will it be? And it turns out there's more to the story, because we know all forms of energy eventually turn into thermal energy. But if there's differences in temperature, we can convert thermal energy to other forms of energy. And this is true on a planetary scale. The sun is hotter than the Earth, and because the sun is hotter than the Earth, the sun radiates energy to us. We radiate energy back to space. Oh yeah, the sun is hot, space is cold, and so we can bring in energy from the sun and radiate it out to space, and this transport of energy through the Earth system basically drives life on this planet. And it's that difference in temperatures that allows life to exist. Okay? It's the differences in temperatures that allow the exchange of radiant energy that allows life to exist on our planet. So it's those differences. So it's not that it's hot or that it's cold that's important. It's the fact that there are places that are hot and there are places that are cold, and that difference allows us to do something. And that's why when I give talks about climate change, I always phrase it this way. I call us a warm planet in a cold universe. We are warmer than the universe, and that allows us to radiate energy outwards. We have a hot sun, a warm planet, and a cold universe. And so as a consequence, we get this flow of energy from the sun to the Earth and back to space that drives life on our planet. It is the differences in temperature, literally, that make life possible. The sun is hot and space is cold, and it's that difference that's important. And so the universe doesn't end in fire or ice. As a matter of fact, if you think about the universe and how it ends in a situation called heat death. And heat death happens when everything is the same. And when everything's the same, there's no way to have these temperature gradients that drive flows, and those are the flows that allow life to exist on our planet. And so it's not, the universe doesn't end when it's hot. It doesn't end in fire. It doesn't end when everything is cold, so it ends in ice. What it ends in is a situation where everything is the same. Everything is the same. And when everything is the same, that's how everything dies. That's the heat death of the universe. And this, I think, is philosophically an extremely important lesson. For this reason, I want to return to the question that we started with. Will the world end in fire or ice? Well, here's my little poem about it. Some say the world will end in fire, some say in ice. But from what I know of entropy, that's not the issue, actually. It's differences that drive the show. When everything is all the same, there's nowhere for the heat to flow, and things that used to just don't go. It's not fire or ice that ends our spree, but a simple lack of diversity. And you know this to be true, and this is something that I just love so much about your generation. You folks understand healthy ecosystems are diverse ecosystems, but you know as well that healthy societies are diverse societies. Our societies are healthy when differences are not just accepted, but respected, embraced, and celebrated. Our diversity is what gives us strength. Our differences are what allows society to live and grow and thrive. And you know this to be true. And this class is wonderfully diverse. And one of the great joys of my existence is that I get a chance to interact with such a diverse, such an amazing, such a talented, creative group of people. I do this, I've talked about this often, out of love. And that is one of the things I love the most about you folks, is the fact that you are diverse and that you understand the importance of your diversity. That is how we live and grow and thrive. And I want to remind you of that fact. And I want to remind you of one more fact, and that is that we are in the middle of an election season. It's hard to forget. Get out and vote. Get out and vote. You know that it's important. This is perhaps the most pivotal election in my lifetime. And so I want to remind you folks how important it is to do that. Make sure that your voice is heard. Thank you very much.